Okay, so here is what it is. This is the straight up definition. It's kind of watered down a little bit. So PMI, or the principle of mathematical induction, is a form of proof for showing a sequence is true for all n, and I'm talking about the way that we describe sequences and n's, in that particular sequence, okay? That's what it is. That's what we're going to call PMI, the principle of mathematical induction. Are you guys okay with that part so far? Okay, so what are we going to be doing today, you guys? We're going to be proving things are true. A very different kind of proof than the geometry proof that you've ever seen before and the algebraic proofs that we've done, okay? Different kind of proof. So I would like you to consider the following sequence, all right? Really dig on the orange and the blue, okay? Let's say I am interested in the sum of the first 5 terms of this particular sequence, and here's the sequence here. Let's do 1 plus 3 plus 5 plus 7 plus 9. And then we could keep going dot, 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 and I'll ask you in a minute what that is. So here's the very first term, here's the second term, here's the third term, here's the fourth term, here's the fifth term, okay? And let's say I am interested in the sum of the first 5 terms. This sequence will keep going, and we will do some more work with it. But for right now, let's just focus on the sum for the first 5 terms, okay? So we're going to do this a couple of ways. The first way that we're going to do this is we're going to do this by hand. This is also called the brute force way. But since there's only 5 terms, we could figure it out. Okay, how much is 1 and 3?
4.
4 and 5?
9.
9 and 7?
16.
And 9. Okay, so we have now verified through basic math that the sum of the first 5 terms is equal to 25. So I'm going to go ahead and put S sub 5 is equal to 25. You guys cool with that part? Okay. The next way that we're going to do this is the formula for the arithmetic sequence. Because after all, would you say that this sequence is arithmetic? Why? Because there is a common, what's the word? There's a common difference. Okay, very good. So we know that the sum of the first 5 terms for an arithmetic sequence will be 5 divided by 2, multiplied by the very first term, which is 1, plus the very last term is 9, because we want the sum of the first 5, right? You guys cool with this so far? It's kind of a review for us, so I'm going to move this up just a little bit more. So therefore, the sum of the first 5 is going to be 5 divided by 2, multiplied by 10. Oh, check that out. Look at that. 50 divided by 2. Yep, look at that. 25. Oh my God, it works. So far, so good. Talk to me, people. Good? Yeah, okay, good. Great. So we did this by hand. We did this by the sum of the arithmetic sequence. Now, I'm going to ask us to look for a pattern. Okay? This is where we're going to extend our thinking a little bit. And let's start with, what would be the sum of the very first term? This is not a trick question. It is that easy. 1. Very good. Okay, good. What's the sum of the first 2 terms? Well, that would be 1 plus 3, which is the number 4. You guys agree with that? Okay. What is the sum of the first 3 terms? That'd be 1 plus 3 plus 5, which would be what? 9. Very good. Does anybody notice anything?
You're squaring the little number.
Oh, you're squaring the little number. This number's squared. That number's squared. Huh. Very interesting. I'm glad that you see that. So this is also 2 squared. This is also 3 squared. This is also 1 squared. Formula still works, right? Does that pattern work? Let's see here. We're seeing a pattern. Let's do the sum of the first 4. Well, that'd be 1 plus 3 plus 5 plus 7, which would be, oh, check it out, 16, which of course is just 4 squared. And then we've already verified 2 different ways. The sum of the first 5 terms is 25, which of course is just 5 squared. So do you guys see a pattern here? I see a pattern. You see a pattern? It's a very simple pattern, but do you see it?
Yeah.
Okay, good. So could I ask you then to extend your thinking? What would be the sum of the first n terms of this sequence?
N squared.
Okay, n squared. Okay, and this is where things become fun for us. Okay, so I'm going to put a little star right here. So the question I have for you is this. Is this statement always true for the sequence that I have laid out, for the one that I have laid out? Is this always true? Induction, or PMI, the principle of mathematical induction, will vouch for this. The principle of mathematics, yeah, I know, whatever. Okay, so PMI is the principle. Okay, what would the nth term of the sequence be? It's arithmetic, right? So if this is a sub 1, if this is a sub 2, if this is a sub 3, how do I describe a sub n? Can we do that, you guys? Yeah, we can, right? So I wonder right now, get how we describe a sub n at your table right now. Okay, so we've just figured out that this sequence can be defined as 2n minus 1. All right, and we are saying that that simply adds up to what? What did we discover? N squared. Okay, now, this is a very, very classic, simple example of the principle of mathematical induction. So what I want to do is I want to take you through all the parts of this, okay? Before we dive into it. Okay, what do you call these things right here? These ones right here, like from 1, 3, 5, what do you call those? Those are just your terms, right? Those are the terms of the sequence. Okay? What do we call this piece right here? Yeah, that's the nth term, right? Very good. Okay, that's how we describe the terms in the sequence, right? So like, for example, if I want the 10th term, it would be 2 times 10 minus 1, or 19, right? You guys agree with that? Okay. And then what are we saying? What is this part over here? This is what we are trying to prove. Okay? So I want you to understand what all the parts are. So that's the nth term, these are the terms. Now this whole thing in orange, that is going to be called our statement. I'll come down here. Okay? So when I am talking about, hey, prove that this is true for the statement, I'm talking about the highlighted part right there. That's going to be our statement, the whole thing. All right? All right, the principle of mathematical induction has 3 steps. You have to show each step every single time, and here are the steps, and we're going to go in order, of course. So here's step number 1. Okay? Step number 1 is to do this, to show that your statement is actually true for the very first term, n equals 1. Okay, so you're actually physically, algebraically showing that the statement is indeed true for the very first term. So what do I mean by that? I mean this. 2 times 1 minus 1, is that the same thing as 1 squared? So do you see what I did? All I did was I plugged in a 1 for that one and for that one, for n equals 1. You guys cool with that? Hello? Yeah, good? Good. So is this indeed true? Yep, check it out. 2 minus 1 is definitely equal to 1. Yep, 1 is equal to 1. Check. Step 1 is done. Step 1 is the easiest of all the steps. So step 1, show the statement is true for n equals 1. All right, step number 2. You have to do this. You have to take a leap of faith and assume your statement is true for some k term in the sequence. All right, and we're going to say, I like to say, k is less than n. So what the heck do I mean by that? Okay, so here's what I mean by this. We're going to assume this. We're going to assume that 1 plus 3 plus 5 plus ... plus up to my k term. Okay, up to k. But how do I describe k in this sequence here? How do I describe the sequence? Well, the sequence is, the nth term is just 2n minus 1, right? So therefore, what would the kth term be? There you go. So we're going to assume up to 2k minus 1 is actually equal to k squared. This is the part that we're assuming is true. So essentially, In step number 2, physically all we're doing is replacing a what with a what? M with a K. And we're saying that K is somewhere along the sequence, right? It's somewhere in the sequence. It could be the 50th term, the 58th term, the 100th term. It's just somewhere along the sequence. We don't know where. We're assuming that up to that point, our statement is true. That's the leap of faith, all right, that we're taking. Now, step 3. This is where we actually prove our statement is true for the next term. Okay, so ladies and gentlemen, if I'm assuming up to K, what's the term to the right of K? K plus 1, okay? So that means K plus 1. Nope, because remember, K is a spot in the sequence. So, okay. So what does that actually look like? Here's what we're saying, okay? We're saying this. We're saying that 1 plus 3 plus 5 plus ... plus 2K minus 1. That's where we stopped, right? In our assumption. So what is the next term after that? The next term after that is 2 times K plus 1 minus 1, and that is an entire term. Now, on the right-hand side, I have to replace K with what? It's the next term, so what would it be? So this would take the form of K plus 1 squared. And I'm going to pause right here to talk about it. All right, so our goal then, you guys, is to make the left-hand side look like the right-hand side. And here's where the fun part comes in. Check this out. See this stuff right here? See that stuff in the green box? Okay. Somebody tell me, what does all the stuff in the green box equal? No, she got it. It equals this, doesn't it? It equals K squared. Because look what it says right there. That's the same green box, isn't it? Okay, so here's the cool part. We now get to replace all that stuff with what?
K squared.
Very good. K squared. Good. Then I need to take care of this piece, so let's clean it up here. This is going to be 2K plus 2, and then I have a minus 1. So what's 2K plus 2 minus 1, you guys?
2K minus 1. K plus 1.
Okay, so I have plus 2K plus 1. And I'm trying to show that that equals this part over here. K plus 1 squared. Does it? Check it out. Factor this piece. This is K plus 1 times K plus 1. Oh, word up. Look at this.
Word up.
K plus 1 squared equals K plus 1 squared. That's the third step we've algebraically shown. It's a very, very basic example, but I'm trying to get the concept across here, okay? So if you guys want to be really fancy, you could do this. Therefore, n is true. Or you say this. Therefore, a statement
What are the 3 dots for?
means therefore is true for all positive integers n. This makes you look really cool. Okay. This is okay, here we go. Second example. Use the principle of mathematical induction to prove the statement is true for all integers n. Okay? So for all integers n. So we have 1 plus 2 plus yada yada all the way up to n. We're thinking that that's just the same thing as n times n plus 1 over 2. We're going to use the principle of mathematical induction to prove this. So, ladies and gentlemen, what is step number 1?
N equals 1.
Yep. And this is how I want you to do it. If you write this out, show true for n is equal to 1. So we literally say this. 1 is equal to 1 times 1 plus 1 over 2. Yep. 1 is equal to 2 divided by 2, which is 1. Yep. Awesome. If it doesn't even work for the very first one, then why bother? But, okay, it's going to work. They're all going to work for this one. I'll leave you that part there. What is step 2? What do we assume? Yeah, we assume that this is true for k, up to k. So I really, actually, physically, yet answer is yes. I want you to rewrite the sequence with a k. 1 plus 2 plus 3 plus yada, yada, yada plus k is equal to k times k plus 1 over 2. Yes, you have to write it in step 2.
Wait, does it have to be true for n equals 1? Right?
Yeah, n equals 1. Yeah, very first step. Okay. Now, step number 3. What's the third step? We prove that this is true for what? The very next term, k plus 1. Okay? So yes, the answer is yes. You have to rewrite it. 1 plus 2 plus 3 plus yada, yada, yada plus k. Now we add on the next term. Okay? What would it be in this case? It'd just be k plus 1. It has that form. Now, what's the form on the right hand going to be? We're going to replace this k right here with what? A k plus 1. So let's do that together. That would be k plus 1. Good. Now we're going to replace this k right here with what? K plus 1. So what's k plus 1 and then a plus 1 inside the parentheses? That would be what? K plus 2. And this is all divided by 2. So that's the structure right there. So I'll highlight the pieces to show you that k became k plus 1, and then that k became this k plus 2 here. Those match up. You guys see it? All right, good. Next, here's the fun part. I always do this. How much is this equal to? It's always equal to the right-hand side of step 2. Always. You see it? All right, good. Now, that means that you can replace all of that with, I'll go orange, with what does it say? It says that that's equal to k times k plus 1 over 2. But then I still have this piece, don't I? K plus 1. And I'm trying to show that it equals that right there. And you can just draw arrows to it the whole time. What's the next move if I'm going to show this is true algebraically? If I want to add these together, what would I do? Common denominator. What would that common denominator be? Yeah, multiply by 2 over 2. Okay? What does that give you then? Oh, well. Number. Okay, it gives you this. K times k plus 1 plus 2 times k plus 1, all divided by the common denominator of 2. Anybody see anything you can factor out? Yeah. These right here, these two terms, that and that, they are the same, right? So you can actually factor them out. K plus 1. What are you left with? Oh, a k plus 2, all divided by 2. Hey, check it out. That's exactly what that says right there. Okay, can we talk about the setup so far, you guys, or you still want some more time to work on it? We're on step number 3 now. Prove it's true for n equals k plus 1. So, how much does all of this equal? What does all that equal to? Yeah, 3 halves k times, right? K plus 1. Good. And then I still have this part, plus a 3 times a k plus 1. Is that true? Yeah. That part? Okay. And we're trying to show that that's equal to this. We'll just go a little arrow here, right? It's trying to show that this is all equal to this right here. Okay, does anyone notice anything about the fact that you have 2 of these right here? Okay, if you have 2 of those, can you factor one out?
Yes.
Yes, you can. You can factor one out. I'll go back to orange. So that will give you k plus 1. What are you left over with? You're left over with this. 3 halves k plus a 3. And we're trying to show that's equal to that. Okay, well, check this out. This piece is still there, is right there. So all I'm going to do is mess with this piece, right? So here's what I'm going to get. Watch, k plus 1. I'm going to factor out a 3 halves because I have a 3 halves factored out there. That leaves me with a k plus 2. Anybody see why? Because the 2's cancel, leaving you with the 3, which is right there, which is exactly what that says up there.